Hello, grade 11s, and welcome to Mindset Learn Extra. I go by the name of Pumi, and today we have our exciting teacher. It is, of course, John. He will be with you, and we'll be having a very awesome time with him today because he is going to be teaching us a lot to know about everything, including, or rather, in physical sciences. Remember, guys, you can always find us on Facebook in order for you to ask questions because John will be answering them, on the show. So the name of the page is www.facebook.com mindset or rather learn extra. That is www.facebook.com/learn extra. We also have a new show coming up. It is really going to be exciting. It is actually a talk show. So if you would love to be a presenter there, please be here on Thursday. For more information, please go on our Facebook page to find out a little bit more about it. Whew, what a mouthful. In any case, here is John with us. Hello, John.
Hi, Pumi. How are you doing?
I'm good. How are you?
Excellent. And it's great to be with you, grade 11s. I was with you a couple of weeks ago, and I'm back again. And you know what? Today we're doing a bit of a consolidation. Last week, Tracy was in to do some stuff on total internal reflection. And today we're going to put together refraction, reflection, and do some calculations. So this is a really key session all about problems that you could get in the exam. So grade 11s, get your pens out, make sure you download the notes. Do you have that website where they can download the notes?
Oh yes, you can go onto www.mindset.co.za and you'll get all of those notes in order for you to learn more.
Excellent. So let's get going and let's get straight into it. As I mentioned, today the topic is refraction calculations, but we'll do a few more of those exam type questions. But let's just quickly do some revision. So what are the things that you must know? And it's really important that you know this. You've got to understand the concept of a refractive index. Every substance has a certain speed through which when light passes through it. So light passes through different substances at different speeds. The ratio between the speed of light in a vacuum and the speed of light through a substance is called the refractive index. We spell it out like this. So there we go. Refractive index, just highlight it for you so you've got it very clearly. The refractive index N of a material is the ratio of the speed c of light in a vacuum to the speed v of light in the material. So it's N is equal to the speed of light in the vacuum, which is equal to c. Remember that c is a constant. Nothing can go faster than the speed of light. Well, that's what we think at the moment. That constant is a value of 3 times 10 to the 8 meters per second. Let me write that down. So we're going to say that it's c, where c is equal to 3 times 10 to the 8 meters per second. And that we need to divide by v, the speed of light through the material. So let's have a look at some of the refractive indices of different materials. So if we start, and we'll try and interpret these. Look at this. The refractive index of air is 1,0. That's saying that the speed of light through air is very close to the speed of light through a vacuum. It is 3 times 10 to the 8 meters per second. Because if we take the speed of light in a vacuum and divide it by 3 times 10 to the 8 meters per second, we're going to get a value of 1. But notice what happens to these other things. Perspex is 1,5. Then ice is 1,3. Let's do the smaller ones first. Ice is 1,3. Notice this number is getting bigger. Then water at 20 degrees Celsius is 1,33. Ethanol is 1,36. The refractive indices are getting bigger. What does that mean when we look at the speed? If this number is getting bigger, n is getting bigger, this is a constant. What is it telling you about this speed? Hope you've got that. If this number is going up, This is staying the same. It's not changing. It's a constant. What's happening to the denominator? Well, the denominator must be getting smaller. It must be going slower. And that's exactly what's happening. In air, light is traveling as quickly as it can in a vacuum, as quickly as it can. As it gets into other medium and it travels through them, traveling through water, traveling through ice, traveling through ethanol, the speed of light in those substances slows down. So how slow can you go? Well, remember, the slowest that light will travel will mean that the index will be biggest. So if we look at this table, there we go. The speed of light through diamond is going to be the slowest. The refractive index is the biggest, but V is going to be slowest. Hope you've got that relationship. The bigger the refractive index, the slower the speed of light in that substance. Now, there's another thing that I need you to understand here. When the refractive index is big, and it gets bigger and bigger and bigger, then we say that it is optically dense. When the refractive index is small, close to 1, then we say this has a low optical density. So small refractive index, let's just make this clear. When the small n, then we can say low optical density. But when we have a large value of n, then we have a high optical density. Okay, so what is this optical density? It gives an idea of the way that the particles in the medium are packed together. But remember, these are all, it's not really density, but it's about how the light moves through this material as well. So it's got to be a material that is transparent or translucent, allows light to travel through it to a certain extent. Materials that are opaque, that don't allow the light to travel through, they're not going to have an optical density. Light's not going to be able to travel through them. So remember those terms. We did go over them earlier in our previous sessions. So what's the next thing that we have to revise? The next important statement is Snell's law. Now, I know that we spent some time on this, and I want to just revise it. Snell's law of refraction. And there are two parts to it. The first part says when light travels from a material with a refractive index N1 into a material with refractive index N2, the refracted ray, the incident ray, and the normal to the interface between the materials all lie in the same plane. So what does that mean? It means if I've got an interface here, and this is air and this is another substance, and I shine a beam of light down onto this interface, then the refracted ray, the incident ray, the normal, and the refracted ray coming out below my hand, if that was the interface, you'd be able to put them on a sheet of paper. They lie in the same plane. The light beam comes in like this. It doesn't then suddenly skew off at an angle. It carries on in the direction that it was going. It bends towards or away from the normal. The normal, the incident ray, and the refracted ray all lie in the same plane. So we can draw them on a piece of paper. That's the important thing. Okay? Next part, and this is the one which we're going to use today, is it tells us the angle of refraction, theta r, is related to the angle of incidence, theta I, by this ratio. The refractive index of the first material times the sine of the angle of the incident ray. So first material is where the incident ray is coming from. So this is N1 here. This is the angle of incidence. Remember, it's with the angle of the normal. So that all makes sense. The N1 goes with that, and it's going to be equal to the sine of that angle. You can show that calculation, but it's not required why it is the sine of the angle. We're not going to do it tonight. You're just going to need to learn the equation. The second thing we're going to say is on the other side of the interface we have N2. Let me change the color of the pen so it makes it clearer. So we've got a second interface, a second material here, and the normal is still there. This is still the normal down there, and the angle of refraction will be this angle here, where that angle is theta r. Now, we're going to use this equation to either find the angle of refraction or to find a missing refractive index. Hope you can see that it's not that difficult. We're just substituting into an equation. Okay, so the focus of today is not doing a whole lot of experiments. We've just done the revision, but I think it's time for us to start doing a few questions. And I'd like to kick off with this particular one here. Question number 1. And it just takes us into a question about reflection. And it is important that we understand this. It says, a light beam strikes a plane mirror. That just means it's a flat mirror. It's not bent, curved, because then something else would happen. This is a flat mirror, a plane mirror. The light beam strikes it so that the angle of incidence is 30 degrees. What will be the angle? Now listen to me carefully here. We've got to check the angle of incidence is 30 degrees. What they're asking is, what is the angle between the mirror and the reflected ray? And you've got to show it on a diagram. So let's do that. Let's get it clear, and let's make sure that we've got it right. So I'm going to use this straight line as the shiny surface of the mirror. I'm then going to say to myself, okay, let's take another line, and I just want to change the color of it quickly and make it white so that we can see it a little bit better, and that's fine. Let's check it now, make sure that we've got a white beam going in like that. Okay, this beam is going to be called our incident ray. And we know that it's heading towards the mirror. The yellow thing is the mirror. Light isn't going to go through it. Remember, a mirror is a shiny surface. It's going to reflect all the light. So the light comes in and it's reflected. Very good. You got that. It's not going to pass through the mirror. It's going to bounce off the mirror. We'll show you that in a minute. Next thing, we need to draw in our normal. Remember, the normal is the line that is at 90 degrees to the mirror's surface. And it is always drawn at 90 degrees, and it strikes at the point of incidence. So we're going to just move it over there. That's the incident ray. I want to just move this one over just a little bit so it is in line at the intersection with the incident ray and the mirror. Now what happens? Well, the law of reflection says that the angle of incidence is equal to the angle of reflection. So if this angle is 30 degrees, this angle is 30 degrees, then where is the reflected ray going to go? Well, the reflected ray is going to start at this point here, and it's going to go at the same angle away from the mirror. Now, I'm not measuring this, I'm just doing it roughly, but what we need to recognize is that the angle of incidence is equal to the angle of reflection. This is the angle, theta r, for reflection. This is theta I for incidence. And for reflection, we know that theta incident is equal to theta r reflected. Now, does that explain the question? Is that what they're looking for? No, let's go back and read the question, because this is a trick question. Let's have a look. What does it say? It says, please find the angle between the mirror and the reflected ray. So here's the mirror and here's the reflected ray. So that's the angle we're looking at. We're not looking at the angle of reflection. So what we've got to do is we've got to remember that the normal is an angle of 90 degrees. That's right angles. It's perpendicular to the surface. So this angle that we're looking for, the green one, I've indicated there, is going to be 90 minus theta r. So we're going to say theta is equal to 90 degrees minus theta r. So that's going to be 90 degrees minus 30 degrees. So the answer that we're looking for is 60 degrees, the angle between the mirror and the reflected ray. Okay, guys, that's been a very quick revision of reflection. Don't forget reflection. You could get asked on it. We're going to move on to ask questions about what happens when light falls on objects. And we're getting into our calculations of refractive indices and reflection. But I think it's time for a break now, don't you?
Yes, most definitely. Guys, please get your glass of water and stick around with us right up until the anchors. When we come back, John is going to be stretching on the topic. We'll be back after this. Welcome back from an ad break, grade 11s. You are still watching Mindset Learn Extra. And guys, please remember that if you have questions on the show today, please post them on Facebook so that we can answer them. And you can always download the notes. Okay, what is this? John, can you explain what is this?
Sure, Pumi. Sorry about that. Guys, I've got a little laser pointer, and I want to use it to show you what's going to happen. Now, a laser pointer emits a little red beam of light, and maybe you can see it flashing off my hand there. Okay? Now, the angle at which it bounces off objects will allow us to show different aspects of what happens when light bounces off different objects. And that's exactly the question we've got here. Notice what it says. It says what we're asked to do is to state the three things that could happen when a ray of light, beam of light, when it falls on an object. Well, it depends on what type of object. So let's just get to our correct piece of information there. It depends on what sort of object we've got. So if we've got a mirror here, now what I'm going to do is I'm going to take my little laser pointer and I'm going to shine it in a particular direction. So I'm going to shine it onto the mirror, and I'm going to reflect it onto Pumi's shirt over there. Okay. So we're not standing in a straight line, but you can see it falling from the mirror, and it's bouncing onto her shirt. That's exactly what we were doing. There's another thing here. We say that when light falls then on an object, it can be reflected. There's another one here. It's a little magnifying glass. Let me put the mirror away. I'll come back to the mirror in a minute. We take the magnifying glass and we put the light beam on it. Then what we'll see is the light beam travels through, and you'll see it reflecting onto or bouncing onto the top of the board here, onto the black section of the board. It's got a little bit smaller. I can even do that and make it go onto Pumi's shirt as well in a straight line this time. The light has traveled through the magnifying glass, through the lens, and you've been able to see the little red dot. This little pointer is producing some red light, which you can see on my shirt, on my hand over there. I don't want to point it into the camera, but they're fun to play with. Now, what's the third thing? So light can pass through, or it can undergo reflection. It was the first one when it fell onto the mirror. So it can undergo reflection, can be reflected. It can pass through an object. We say that when it does that and it passes through a material that's transparent or even slightly opaque, then it is undergoing refraction because it's changing its speed. It's slowing down. Or if it's going from a dense medium, optically dense medium, to a less optically dense medium, it will speeding up. So it can undergo refraction, it can be reflected, it can be refracted. Better to say refracted. And what's the third thing? Well, guys, this is important. We had a long discussion about this when I was with you 2 weeks ago. We said that objects that are dark in color, black objects, they absorb light. Now, the same goes for colored materials. They absorb certain frequencies of light and they reflect the ones that we see. So the light can be refracted, it can be reflected, and it can be absorbed. So light falling onto a black object, all the light is absorbed, all the frequencies of light are absorbed, and we don't see any reflection. When something falls onto a blue object, only the blue light is reflected. All the other colors, all the other frequencies of light are absorbed. Okay, so I think that covers that section. Let's now make sure that we get Snell's law and the idea of refractive index sorted out. So here's the question. See if you can work along with me, because we're going to do quite a number of these calculations. We've got a whole lot. Make sure you download the notes. They're on the Learn Extra page on the www.learnextra.co.za/live. Go and download them. Make sure you work through them. So what does it say? It says light is shone through a sapphire. Calculate the speed of light when light travels through the sapphire. Now, guys, we can't do this unless we get the refractive index. What information are we given? Let's write down. We know that the refractive index, N, is equal to C divided by V. And what they want us to do is they want to calculate the speed of light. This is the V part. Now, we know that C is the speed of light in a vacuum. It's 3 times 10 to the 8 meters per second. But what we need now is to find the refractive index of sapphire. Now, if you remember, we had a whole table of them. I've just made a copy of that table. Let's go and have a look if we can find sapphire on it. There it is, right at the bottom. Sapphire is 1,76. 1,76. Pumi, will you remember that for me?
Oh, yeah.
1,76 if I need it. So the refractive index of sapphire was 1,76. Okay, now guys, what we're wanting to do is to find V. V is our unknown. V, remember, is the speed of light through the sapphire. That's exactly what we want to find. So how are we going to go about it? This is how I always work. I say, we've got a formula, can get it on the data sheet, substitute into the formula. Don't mess around. If you try and change the formula and you make a mistake, then you're not going to get your marks for substitution. Substitute in first and then solve. So let's substitute. Here we go. We're going to say the refractive index of sapphire, 1,76. What was the speed of light? 3 times 10 to the 8 meters per second. You must learn that. It's on the data sheet, but you must learn it as well. And we want to find V. That's what we're looking for. So we can now, having substituted, recognize, multiply both sides by V, and then say divide by the refractive index. So it's 3 times 10 to the 8 meters per second divided by 1,76. I'm going to need a calculator to do that, and my calculator has disappeared. So let me quickly get it up. It's just going to take a second. There's my calculator. Quick dash to try and get it. We just simply plug the values into the calculator, and we'll make sure that we get the right answer. Are we ready to get the calculator? There we go. We're not going to worry. There's my calculator, and we're going to put the values in. 3 exponent 8 divided by 1,76 equals, and that's a really big number, but I must write it in scientific notation. So what I'm going to do is I'm going to divide this by 1 times 10 to the 8, because I can count the number of places there. 1 times 10 to the 8, and if you then look at the answer, you will get it as a fraction 1,70 times 10 to the 8. 1,70 times 10 to the 8. So make sure you with that, you've got that sorted out. 1,70 times 10 to the 8. We don't want to meters per second. Guys, it's not going to be less than times 10 to the 8. We need to make sure, it's very unlikely that it's going to be very, very much smaller than that. The refractive index wasn't that high, so we can predict, yeah, we think that that's about right. If it was 2, the refractive index was 2, then we know that the speed of light is going to be about half of what it was before in a vacuum. So that's how I know that this is about the right value, because it's close to where we were. With a refractive index of 1,76, we are just about there. We're in the right region. Okay, make sure you don't make a mistake. Calculate carefully and get your answer correct. Working with scientific notation isn't easy, and it's something that you're going to need to practice. Let's move on and let's see what our next calculation is. Okay, here we go. This one tells us something a little bit more. It says, when light moves from glass to diamond, will the speed increase, decrease, or stay the same? Give a reason for your answer by referring to the refractive index and the optical density of each medium. Okay, so guys, that's really important. We've got to take the data and look at them very carefully. So let's go to our table. We want the refractive index of glass and diamond. Where's our table of refractive indices? There they are. And I can see diamond over here. Diamond at a value of 2,42. And glass, where's glass? 1,52. So glass is 1,52 and diamond is 2,52. So let me write that down. 2,42 for diamond. So refractive index of diamond (2,52). Okay, let's just check it. 42, thank you. I wasn't listening very carefully. I didn't remember that. Make sure that you write it down correctly. So diamond is 2,42. What about glass? So we need the refractive index of glass. Check it on the table. And there it is, 1,452. That's where I was making the distinction. 1,52. So guys, let's make sure we understand what this is meaning. Which one is going to slow the light down the most? Remember, the higher the refractive index, the slower the light will travel. So immediately we can see that here is where the light is going to be slowest. Slowest, and here it's going to be slightly faster. It's going to be faster, but slower than in a vacuum. So slower, this one is going to be fast, this one is going to be slowest. Got it? What do we have to do? It's moving from glass to diamond. So it's going from fast to slowest. What's happening? Is it increasing, decreasing, or staying the same? Now, I think we can definitely say that this is going to decrease. So the speed of light decreases. And why? Because it's moving from, because the optical density in glass is less than the optical density in diamond. Sorry, the refractive index. The refractive index of glass is less than the refractive index of diamond. And we can say that it is optically, because we have to do density, optically less dense to optically more dense. Diamond is more dense, more dense. Okay, Got it? Make sure that you understand what's happening when light changes and moves into different medium. It's going to change its speed. That's what refraction is all about. Now, the other effect is that light, when it's refracted, changes direction. Our next little problem is going to deal with that. We've got a table here, and I want to just brief you on the table, and then we're going to take a break and we'll do some calculations with this. So, light moves from substance 1 through substance 2, then through substance 3 until it reaches substance 4, and it will move out into air. Refraction takes place at each of the surfaces. The following information is given. So, what they tell you is the speed of light. They don't give you the refractive index. They then tell you the refractive index, but they don't give you the speed of light. They then give you the speed of light, but they don't give you the refractive index. They give you the refractive index, but they don't give you the speed of light. How are we going to do this? Well, remember the formula that we're going to use is N is equal to C over V. Let's just do the first one and make sure that you've got it right, or the first two. Make sure you've got it right, and then we'll put up the answers for the others after the break. Give you a chance to check yourself as well. So, for number 1, very important that we get this right. Speed of light, 3 times 10 to the 8 meters per second, divided by the velocity. They've given it to you 2,5 times 10 to the 8, like that. Let's work out the refractive index. Go to our calculator. There we go. 3 exponent 8 divided by 2,5 exponent 8 is equal to 6 over 5, which if we push the calculator will give us 1,2. So the answer we're looking for, the refractive index here for substance 1, is 1,2. I'm going to fill it in over here, so we've got it. 1,2. Right, let's do the second part. We want to find, for part number 2, what is the velocity in the medium. What's the velocity in the medium? Again, we're going to use N is equal to C over V. And here we're going to substitute, and we're going to say, we know the N this time. We know the N. The N was 2,5. So we're going to put in 2,5. We're going to say C was 3 times 10 to the 8. And we're going to find V. We're going to say that V, therefore, V is equal to 3 times 10 to the 8 divided by 2,5. Now, let's do the calculator. Clear it. 3 exponent 8 divided by 2,5. And we're going to get a very big answer with lots of zeros. I'm going to check the number of places. I believe it's going to be times 10 to the 8. I divide by 1 exponent 8, and you're going to get that answer, 1,2. But remember, that's not 1,2. It's 1,2 times 10 to the 8 equals 1,2 times 10 to the 8 meters per second, like that. Guys, I think we can fill it in on the table. Use the eraser. Put that one in there. We're going to say, here we go. We have got 1,2 times 10 to the 8 meters per second. What do you think the values of the next two are going to be? Have a careful look at them. Can you predict what's going to happen? Well, look at this. The speed here is getting less. The speed is getting less. What do you think is going to happen to the refractive index? Is the refractive index going to be more, or is it going to be less? What's going to happen if I go to a refractive index of 1,8? Is the speed going to increase or decrease? Look at it carefully, and we're going to do those calculations and fill them answers in with our predictions as soon as we get back from the break. Is that okay, Pumi?
Yes, it's definitely okay. Guys, please do remember that you can also be a future star. So all what you have to do is just to enter the competition. But right now, let's take a break. We'll see you after this. Welcome back, guys, from an ad break. You are still watching Mindset Learn Extra. John is definitely helping us with physical science. We are having fun. Thank you so much for those Facebook messages and comments, or rather notes or questions that you have for us. John will be answering them. But right now, John, take it away.
Okay, Pumi, thank you so much. Guys, I hope you've been able to work through what I asked you to have a quick look at. Can you make a prediction about what's going to happen here? Let's look carefully. What we notice is that when the speed was 2,5, then the refractive index was 1,2. Now look what's happened. The speed has changed. It went from 2,5 to 1,2. So that means the speed decreased. There was a decrease. But what happened to the refractive index? Notice the refractive index increased. So what's going to happen when we go from 1,2 to 1,1? Notice this is also a decrease. So the trend, we'll expect that the refractive index here is going to be bigger. It's going to increase. We'll check that in a minute. We want to now check what's going to happen if we go from a big one to a small one. So if we go from a big to a small, then I guess that's a decrease of refractive index. Okay? And it means that the speed here must increase. They are inversely proportional. As this one goes down, this one is going up. When the speed goes down, goes up, then the refractive index goes down. That's going to be really important. So we're going to expect here a bigger answer, bigger than 1,1, and here we're going to expect a bigger one. Let's go and check it out. I've already, in the break, just did the calculation for us, and we'll work through it. So we said there was the 1,1, we substituted it in, and look what we got, a refractive index of 2,73. Refractive index 2,73. And notice our prediction is absolutely right. We said it's going to be bigger. So it's 2,73, which is true. It's bigger than 2,5. Now, what do we expect with the speed? Let's see what's happened to the speed. Is it going to be bigger than 1,1 or not? Well, there's the calculation, and there it is. 1,76. Notice I wrote down the formula, substituted the refractive index, substituted the speed of light, solved for V, and I get it as 1,76 times 10 to the 8 meters per second. So I'm going to put that in here, 1,76 times 10 to the 8 meters per second. Got it. Now, fortunately, this isn't the last part of this question. We have to use this table of information to decide what's going to happen when the beam of light travels through this different material. Let's have a look at the second part. This is the interesting part to refraction. Change of speed, but then there's also the change of direction. So here's the incident ray. This is the incident ray. And all that we've got to recognize is the refractive indexes. This was substance 1, the one that we've just worked out. That's substance 2, that's substance 3, that's substance 4, and I've just put in an extra one to say air. Now, guys, the first thing I'm going to do is I'm going to draw in the normal. And I'm just going to draw the normal in freehand and draw it in like that. And say to myself, right, what's going to happen if I have a refractive index of 1,2 and I've now got a refractive index of 2,5? What's happening to the speed? It's very important that you understand this. The refractive index was 1, 2, which is close to 1. It's close to the air. It's probably water, or it's one of those liquids where the light is traveling through. Now we've got a refractive index of 2, 5. That's something high optical density. Need to recognize that when the refractive index is increasing, what's happening to the speed? I'm going to put the speed in green. What happens to the speed? The speed goes from here to here. It will decrease. Now, in terms of Snell's law, what we know is that there's the relationship of the angle. We could calculate the angle. But what you need to recognize is that this yellow beam of light that we have over here is not going to carry on in that direction. It's going to change direction. It's not going to carry on. It's going to bend towards the normal. It's slowing down, and so it will move towards the normal. And we draw the actual beam in, not in that position where I had it, but I'm going to just move it and draw it so that it's a smaller angle. It decreases in size, and it moves towards the normal. So as it gets slower, it moves closer to the normal. I want to just add that as a writing over here so you remember. It moves towards the normal. Bends towards the normal. Okay, let's put another normal in over here, where the interface is now between substance 2 and substance 3. What's the trend? We recognize that the refractive indices are increasing. What does that mean? It means the speed of light, it's decreasing, it's slowing down. So from here to here, it decreases, it slows down. And if it slows down, which way does it bend? Well, you've got it. It will do the same as what it did before. It gets even smaller. The angle of refraction is even smaller. It will bend closer to the normal. Now, my beams aren't really very clearly aligned. Let me align them so that we've got it something like that, and that's better. Right, now what's going to happen? It's moving from 2,73 to 1,8 as a refractive index. This means it's decreasing. It's getting smaller. It decreases. So what happens to the speed? You got it. It's going to speed up. And if it speeds up, let's draw in our normal. In which direction does it bend? That's not a very clear normal as a dotted line. Let me just draw the dotted line a little bit closer to where it should be. Let's move it a little bit closer. That's good enough, I think. No, I'm picking the wrong one. So let's just try again. There we go. Move it in. Okay, I'm going to leave it. Move that way. Which way is it going to bend? It's not going, because it's speeding up, it's going to change direction. It's not going to bend towards the normal. It's going to bend away from the normal. It's going to get bigger. The angle of refraction is going to be bigger than the angle of incidence. So let's draw that in. So here we go. We're going to draw it in, and we're going to say it's going to get bigger. And now the last one. If we move from substance 4 to air, what's going to happen? Substance 4 to air, well, the refractive index of air is 1, 0. So I hope you can see that that's also a decrease in refractive index, but it means that it's a huge increase in speed. And so, again, which way is it going to bend? It's going to bend away from the normal, and we'll draw it like this. Now, if you're drawing it in your books, then you would be able to use a protractor. You'd actually be able to measure the angle of incidences, and we'd use Snell's law to do that. I'm just illustrating it and showing you that this refractive index, it's not going to carry on in the same direction. This line doesn't carry on like that. doesn't bend towards the normal, it bends away from the normal, so that the angle of refraction here gets bigger. Notice there the angle of refraction got bigger, where in the first two, the angle of refraction got smaller than the angle of incidence. Guys, there are a whole lot of relationships that you need to understand. You need to be able to draw these diagrams very carefully and make sure that you've got them. We're going to do one last problem now, or situation, where we're going to use Snell's law. So let's make sure that we get this right. It tells us to calculate the refractive index of a diamond, or it says calculate the refractive index of a diamond is an angle of incidence of 30 degrees, causes an angle of refraction of 12 degrees when light moves from air into the diamond. Okay, so what we have to do is to calculate the refractive index of a diamond. If we know that the angle of incidence is 30 degrees, it causes an angle of refraction of 12 degrees. Let's put down everything that we've got. We know that light is moving from air. N1 is air. And we know the refractive index is 1,0. We know that it's moving into diamond. And that's what we're wanting to find. That's N2. We don't know what that is. What else are we told? We're told the angle of incidence is equal to 30 degrees. We're told the angle of refraction is equal to 12 degrees. So how are we going to work this? Well, you should remember that right in the beginning, we said Snell's law. Let me just remind you. So over here, Snell's law said N1 sine theta, N1 sine theta I is equal to N2 sine theta R. Let's write down the equation and make sure that we've got it right. So we're going to say N1 sine theta I is equal to N2 sine theta R. Now we've set it up. All we've got to do is take our values and substitute them in to find the unknown. Very straightforward. So let's take the values that we've got given over there, and we're going to substitute them in. So first thing, let's put in 1,0. Now guys, I know that you might be tempted not to put the 1 in, because 1 multiplied by anything, Pumi? 1 multiplied by anything?
It's 1.
No, it's the thing, isn't it?
Oh, it's the thing,
Yeah,
yes. Yeah.
So we know that
50,
multiplying
yeah.
by 1 doesn't change much.
Oh, yeah.
We must show it. Okay? We know that this is sine theta I, which was 30 degrees. Okay? And we want to find N2, and we know that is sine of 12 degrees. So, rearranging, notice I've put everything in, and I've even put this side, the left-hand side, in brackets. I'm going to divide both sides by sine of 12 degrees. To get N2, therefore, we can say N2 is equal to 1,0 times sine of 30 degrees divided by sine of 12 degrees. All I need to do is to use my calculator. So let's get it clear, and we're going to say, first of all, let's take sine of 30 degrees. I'm not going to multiply by 1. I'm going to say sine of 30 degrees divided by the sine of 12 degrees. 12 degrees. There we go. And what do you know? It gives me a number 2,4048, so on. So what am I going to say? 2,40 equals 2,40. That's the refractive index of this diamond. Okay? So what we need to recognize, maybe it's not the refractive index. If you remember when we looked at the table, we had 2,42 as our refractive index over here. But different diamonds could have slightly different refractive indices. So the calculated value we've got as 2,40. Remember, could also be that we've made a slight calculation error because of measuring the angle. The angle might have been 30,01 or 12,02, something like that. Small error why it's not 2,40. Guys, been great being with you. Pumi, thank you so much.
Thank you so much, John. All right, okay, guys, thank you so much for watching the show today. John has been really helpful today with the show, and I hope that he's helped you so much as well. In any case, guys, thank you so much for watching. This has been Mindset Learn Extra. Bye-bye.
In those substances slows down. So how slow can you go? Well, remember, the slowest that light will travel will mean that the index will be biggest. So if we look at this table, there we go. The speed of light through diamond is going to be the slowest. The refractive index is the biggest, but V is going to be slowest. Hope you've got that relationship. The bigger the refractive index, the slower the speed of light in that substance. Now, there's another thing that I need you to understand here. When the refractive index is big, and it gets bigger and bigger and bigger, then we say that it is optically dense. When the refractive index is small, close to 1, then we say this has a low optical density. So small refractive index, let's just make this clear. When the small n, then we can say low optical density. But when we have a large value of n, then we have a high optical density.
Hello, grade 11s, and welcome to Mindset Learn Extra. I go by the name of Pumi, and today we have our exciting teacher. It is, of course, John. He will be with you, and we'll be having a very awesome time with him today because he is going to be teaching us a lot to know about everything, including, or rather, in physical sciences. Remember, guys, you can always find us on Facebook in order for you to ask questions because John will be answering them, on the show. So the name of the page is www.facebook.com mindset, or rather learn extra. That is www.facebook.com/learn extra. We also have a new show coming up. It is really going to be exciting. It is actually a talk show. So if you would love to be a presenter there, please be here on Thursday. For more information, please go on our Facebook page to find out a little bit more about it. Whew, what a mouthful. In any case, here is John with us. Hello, John.
Hi, Pumi. How are you doing?
I'm good. How are you?
Excellent. And it's great to be with you, grade 11s. I was with you a couple of weeks ago, and I'm back again. And you know what? Today we're doing refractive index. Just highlight it for you so you've got it very clearly. The refractive index N of a material is the ratio of the speed C of light in a vacuum to the speed V of light in the material. So it's N is equal to the speed of light in the vacuum, which is equal to C. Remember that C is a constant. Nothing can go faster than the speed of light. Well, that's what we think at the moment. That constant is a value of 3 times 10 to the 8 meters per second. Let me write that down. So we're going to say that it's C, where C is equal to 3 times 10 to the 8 meters per second. And that we need to divide by V, the speed of light through the material. So let's have a look at some of the refractive indices of different materials. So if we start and we'll try and interpret these. Look at this. The refractive index of air is 1,0. That's saying that the speed of light through air is very close to the speed of light through a vacuum. It is 3 times 10 to the 8 meters per second. Because if we take the speed, a bit of a consolidation, last week Tracy was in to do some stuff on total internal reflection, and today we're going to put together refraction, reflection, and do some calculations. So this is a really key session, all about problems that you could get in the exam. So grade 11s, get your pens out, make sure you download the notes. Do you have that website where they can download the notes?
Oh yes, you can go onto www.mindset.co.za and you'll get all of those notes in order for you to learn more.
Excellent. So let's get going and let's get straight into it. As I mentioned, today the topic is refraction calculations, but we'll do a few more of those exam type questions. But let's just quickly do some revision. So what are the things that you must know? And it's really important that you know this. You've got to understand the concept of a refractive index. Every substance has a certain speed through which when light passes through it. So light passes through different substances at different speeds. The ratio between the speed of light in a vacuum and the speed of light through a substance is called the refractive index. We spell it out like this. So there we go. Speed of light in a vacuum and divide it by 3 times 10 to the 8 meters per second, we're going to get a value of 1. But notice what happens to these other things. Perspex is 1,5. Then ice is 1,3. Let's do the smaller ones first. Ice is 1,3. Notice this number is getting bigger. Then water at 20 degrees Celsius is 1,33. Ethanol is 1,36. The refractive indices are getting bigger. What does that mean when we look at the speed? If this number is getting bigger, n is getting bigger, this is a constant. What is it telling you about this speed? Hope you've got that. If this number is going up, this is staying the same. It's not changing. It's a constant. What's happening to the denominator? Well, the denominator must be getting smaller. It must be going slower. And that's exactly what's happening. In air, light is traveling as quickly as it can in a vacuum, as quickly as it can. As it gets into other medium and it travels through them, traveling through water, traveling through ice, traveling through ethanol, the speed of light